Okay guys, this is our first discussion in Unit 9 and we're going to talk sort of about solutions in general, do a little introduction in terms of some vocabulary and then also in terms of some calculations. So just to start, I want to look at these four solutions. Now when we think of solutions, a lot of times we think about something like sugar dissolved in water, and that's a very common solution, but really solutions can be a much broader class of things, right? We can have, it doesn't just have to be a solid dissolved in a liquid, we could have a solution of two liquids, a gas in a liquid, even multiple gases. So a solution is just another way of saying a homogeneous mixture. So I want you to look at these four and think about what the solute and the solvent would be based on your knowledge of those words. So when we think about chocolate milk, the solvent, what we're dissolving something in, is probably the milk, right? And the solute is chocolate, either chocolate syrup or that crazy chocolate powder that gets all over the place. Carbonated water, the solvent would be water, and the solute would be carbon dioxide. In ocean water, the solvent, again, is water. The solute, well, I mean, there's lots of solutes in the ocean, but salt would be a primary one. And then in air, that's a little trickier, right? Because we don't really think of air as a solution, but it is a homogeneous mixture. So if we had to pick something that was the solvent, and again, usually when we talk about solvents, we mean a liquid, but it applies here as well. We could think about nitrogen as a solvent because it's the primary component of air, and solutes would be things like oxygen, CO2, argon, etc. All right, so we're going to talk about how we make solutions, how we dilute solutions, and how we express concentration in this discussion. All right, so what is a solution? A solution is basically, as simply as I can put it, it's just one thing dissolved in another. The most common thing you'll see again is a solid dissolved in a liquid, but really both the solute and the solvent could be any state of matter. A solution forms when the solute is dissolved in the solvent. For example, if an ionic salt dissolves in water. And the main factor that's going to affect the extent of dissolving is the temperature and also the rate. Also, how much you stir it is going to affect the rate of dissolving. So if I just let it sit there, it's going to dissolve more slowly than if I stir it rapidly. Okay. Now, high temperature is going to increase the solubility of a solid in a liquid. Low temperature will increase the solubility of a gas in a liquid. You probably kind of instinctively know this, right? If you've ever had a carbonated beverage and you're drinking it on a hot day and you left it in the car while you went into a store, when you come back out of the store, your carbonated beverage is going to not be so great anymore because it's gotten really hot. So the solubility of the CO2 has decreased. Okay, so let's talk about some vocabulary. A solute is basically the minor components, the component we have less of, and it's dissolved in the solvent. The solvent is the major component, and it dissolves the solute. Now, the most common solvent you're going to see is water, and we actually call this the universal solvent. That's kind of a misnomer. Universal solvent would imply that water dissolves absolutely everything, and we know it doesn't, right? You know that oil doesn't dissolve in water, for example, but water does dissolve many, many things, and it's probably our most common solvent. So when we say something is soluble, that just means that a solute has the ability to dissolve in a given solvent. So we might say that salt is soluble in water because it will dissolve, but we would say that oil is insoluble in water because it won't dissolve in water. Now, one word that you'll hear a lot is an electrolyte. And an electrolyte is something that contains ions. So when it's dissolved in water, it's going to conduct electricity. A strong electrolyte is going to completely dissociate into ions and weak only partially. So if you have a strong electrolyte in water, it'll conduct more than a weak one. Now, you've probably heard this term most in terms of things like Gatorade and Powerade. They say they contain electrolytes. Yeah, that's just a fancy way of saying that they have salt in them. So it sounds super fancy and high tech, but really it just means it has ions in it. Okay, so what you see over here on the right is a graph that tells you the solubility of different substances. So on the y-axis, it tells you the grams of solute, per 100 grams of water that can dissolve. And on the x-axis, it's for a given temperature. Now you notice that most of them increase as temperature increases, and that's because mostly what we have here are solids. But one thing you might notice is that ammonia here, NH3, its solubility decreases as temperature increases. So pause for a minute and think about what that probably means about ammonia based on what we've already said. So if you were thinking that that probably means that ammonia is a gas, you'd be correct. And so remember, at higher temperatures, gases are less soluble. Now, solubility, again, is the degree to which something dissolves. So even though all these things are to some extent soluble in water, some of them are more soluble and some of them are less soluble. Potassium iodide up here, very soluble in water, but something like potassium chlorate down here is less soluble. An unsaturated solution exists when the solution holds less than its total capacity of solute at a given temperature. So let's say I had water at 30 degrees Celsius and I only had 70 grams of sodium nitrate. Because that's less than the maximum capacity of sodium nitrate, that means it's unsaturated. Saturated solution is when a solution holds total capacity of solute at a given temperature. And so if I add any more solute, it's not going to dissolve. Okay, so for example, again, I'll use sodium nitrate because it's a little easier to see up here. At 30 degrees Celsius, if I had, 96 grams of sodium nitrate dissolved, that would be a saturated solution. Now, a supersaturated solution occurs when the solution somehow has more than its total capacity of solute dissolved at a given temperature. So you might think, how is that possible? How could a solution possibly hold more than its maximum? Well, the way that we make a supersaturated solution is that we heat it up. Okay, so we saturate a solution at a higher temperature and then slowly cool it. And so that solute will remain dissolved even though it has now more than the maximum at that given temperature. Now, a supersaturated solution isn't very stable. If you add one crystal of the solid, it'll a lot of the solid will come out of the solution. So that's how rock candy is made. You supersaturate a solution of sugar and then add a crystal, and the sugar crystallizes on like a string or something. All right, so when we talk about solution concentration, we express concentration using something called molarity. So molarity is the moles of solute per liters of solution. So that's the total volume of the solution, okay? This is sort of similar in a way to density, except with density we're talking about mass over volume. Here we're talking about moles over volume. Now the units of molarities are mole, you can just say moles per liter, or sometimes we use a capital M, and that capital M means moles per liter. Okay, so just for convenience and speed, you can use the capital M. So let's look at two examples where we're calculating molarity. So the first is to calculate the molarity of 0.060 moles of sodium chloride in 1.5 liters of solution. So molarity is the moles of solute over liters of solution. So we would divide the moles by the liters and we get 0.040 molar, capital M. You could also use moles per liter as your units there. Now note that my answer has two significant digits. Both numbers actually here have two significant digits. This is a reminder that leading zeros are not significant. So 0.060 has two significant digits because trailing zeros count when there's decimal place present. All right, so let's look at the next example. The next example says, what is the molarity of 250 milliliters of a solution containing 1.55 grams of potassium bromide? And I gave you the molar mass. Now, again, molarity is moles per liter. So we need to get moles and then we need to get liters. The liters seem pretty easy, right? If I have milliliters, it's trivial to convert that to liters, but I am gonna have to convert the grams to moles. So let's go ahead and do that, okay? So when I convert the grams to moles, I get 0.0130 moles of potassium bromide. And then to get the molarity, take the moles divided by the liters, and I get 0.052. Okay? All right, so let's talk about preparing a solution. Now, this is a skill you would do in the lab, but it's important to be able to do this, right? We're very rarely asked to calculate molarity of a solution given moles and liters, because in the lab we would typically measure something out in grams. And a lot of times a skill that we're asked to do is to prepare a solution of a given concentration. So if I wanted to make 0.1 liters or 100 milliliters of a 0.1 molar copper chloride dihydrate solution, the first thing that I'd have to do is weigh out the number of grams that I need. So I have to figure out how to calculate that, okay? So here's how I would do it. I know that molarity is moles per liter, okay? And here in the problem, I'm given the molarity and I'm given the volume. So I can solve for the number of moles. So basically, I need 0.01 moles of copper chloride dihydrate in this solution. So then using the molar mass, I can find that I need 1.70 grams. Now, you might be wondering why I'm ignoring sig figs here, because both of these have one significant digit. But my goal here when I'm trying to make this solution is I want to make it as precise as possible. So after I made the solution, I could go back and figure out how many significant digits were in my molarity and my volume. Okay, so my balance goes to 2 decimal places. So when I'm figuring out how to make it, that's how far I would go. Okay, and when you actually make a solution, there's sort of a right and a wrong way to do it, right? You don't just want to throw 1.7 grams of copper chloride into 100 milliliters of water, because remember that that is the total volume of the solution with both the copper chloride and the water. Now here, that's a pretty small amount, so it wouldn't make a huge difference, but still you should try to make it correctly. So first you would dissolve the solid in a beaker with distilled water. And it's the reason we would do this in a beaker rather than a graduated cylinder is it's much easier to stir and to get it to all dissolve. Then pour that solution into a graduated cylinder and fill the graduated cylinder to the desired volume with distilled water. So when you dissolve the solid, you'd want to make sure you used less than 100 milliliters of water. Okay. Now, let's think about diluting a solution. You've probably all done this if you've ever made Kool-Aid or any kind of like beverage from a mix, right? You take the powder and you put in some water and then you put in some more. So imagine that you were trying to make lemonade from a mix and it was way, way, way too sweet and strong. And so you decided to add more water. What you're doing there is you're diluting the solution, right? So when we dilute a solution by adding water, we decrease the concentration, right? That's the whole point, is to make there be fewer moles of the solute in a given volume. So the amount of solvent increases because that's how we dilute a solution, right? We add more water or whatever the solvent is. Now, imagine again diluting some kind of beverage by adding water. What happens to the number of moles of solute when we dilute the solution? Well, nothing. Okay, it doesn't change at all, right? We didn't change the amount of beverage powder that we added. So when we dilute, we could say that the moles in the initial solution are equal to the moles in the final solution, right? Now, using the molarity formula, we know that moles is equal to molarity times volume, right? Since molarity is moles over volume, that is how you can rearrange that equation. So if that's true, then that must also be true. When we do a dilution, the initial molarity times the initial volume is equal to the new molarity times the new volume. Okay, so let's look at this sample problem. If you dilute 20 liters of a 3.5 molar solution to make 100 liters of solution, what is the molarity of the new dilute solution? Now, before I solve this problem, I'm going to take just a second and predict what I think my answer is, okay? I know that my solution that I'm making is going to be more dilute, so I expect the molarity to go down. So if I get a number for my final answer that's higher than 3.5, I want to go back and check and make sure I've done this correctly. Okay, so I know this is a dilution, so I'm going to start by writing my formula. I think it's helpful at that point to go ahead and pull out all the numbers and assign them to variables. So my initial molarity is 3.5 molar. My initial volume is 20 liters. I'm trying to find my new molarity, and my new volume is 100 liters. Then I can substitute in my numbers, and when I solve, I'll get that my new molarity is 0.7 molar. And that makes sense, right? Because it's lower than my initial molarity of 3.5, and I diluted it by a factor of 5, right? So that makes sense. All right, so pause for just a moment and try these two problems. The first is just a straight up molarity calculation, and the second is a dilution. So pause for just a second, try these, and then we'll go over them. Okay, So for the first problem, we have moles and we have liters, so all we have to do is divide them, and you would get 0.19 molar. And I rounded to 2 significant digits here because 1.5 liters has 2 significant digits. For the next one, this is a dilution, so I'm going to use my dilution formula. I figured out which numbers corresponded to which variables, and then I can substitute in. Now, one thing I want to sort of draw your attention to is making sure you pair up the volumes and molarity correctly. Sometimes if you're just rushing through this, you might be like, okay, well, my first molarity is 4.5, my first volume is 0.5, and my new molarity is 3. But you have to read carefully. I want to find the volume of the 4.5 molar solution, so 4.5 and my unknown need to be on the same side of the equation. And then when I substitute, I would get 0.33 liters. Now, we can also use molarity to solve stoichiometry problems. So since molarity is intensive, and what we mean by that is that if I have a 1 molar solution, the molarity of 5 milliliters and the molarity of 100 milliliters, it's the same. We can use it as a conversion factor in dimensional analysis. Okay, so let's look at this sample problem. This is the reaction of calcium hydroxide and sulfuric acid to make calcium sulfate and water. So the problem says, if the sulfuric acid has a concentration of 0.82 molar, how many liters of it are needed to react with 5.5 moles of calcium hydroxide? Okay, so initially this seems like kind of an overwhelming problem. But remember when we do stoichiometry, how we proceed, all right? We start by writing what we're given. Now, it looks like you have 2 givens in this problem, but we're going to use molarity as a conversion factor, so we're going to start with 5.5 moles as our given. Now remember, whenever you do a stoichiometry problem, you have to convert your given into moles, do a mole ratio, and then convert to your desired units. Okay, so I have 5.5 moles as my given. I'm going to use my mole ratio to convert to moles of sulfuric acid. And then I want to know the volume of sulfuric acid. So I'm going to use molarity as a conversion factor here to get to volume, okay? Because if it's 0.82 molar, that means that there are 0.82 moles of sulfuric acid for every 1 liter, okay? So the 0.82 goes with the moles, and that's per 1 liter. Now, people sometimes have a really hard time using molarity as a conversion factor. So if you prefer, you could just use dimensional analysis to convert to moles of sulfuric acid and then use the molarity formula, right? Since you know the molarity and the moles. Either way works just fine. It's sort of a matter of personal preference. Okay, so try these 2 problems and then we'll go over them. There's multiple ways to do them, and I'll sort of talk about how you could approach them. You can either try to use the molarity formula, or you can try to do the whole thing with dimensional analysis. So pause for just a minute and then we'll go over them. Okay, so let's look at this first problem. It says, what mass of calcium carbonate is needed to make 1.2 liters of a 1.7 molar calcium carbonate solution? So here we're not actually trying to do stoichiometry. We're really just doing conversions, okay? So here's how I set it up. I started with 1.2 liters, and then I used the molarity to convert to moles. If it's 1.7 molar, that means there's 1.7 moles in 1 liter. Once I had moles, then I used the molar mass to convert to grams, and I got 204 grams of calcium carbonate. Alternately, you could use the molarity formula to solve for moles, and then you could just convert those moles to grams, okay? Now, it says what volume of a 3.0 molar hydrochloric acid solution is needed to completely react with the amount of calcium carbonate in part A. So this is where we're going to have to do stoichiometry with a mole ratio. So you can use the molarity to convert to moles of calcium carbonate. If you just use the molarity formula in the first question to find the moles, you could start there. Then I'm going to do my mole ratio to convert to moles of hydrochloric acid. And then I can use molarity of hydrochloric acid to convert to liters. So when it says that it's 3.0 molar, that means there are 3 moles of hydrochloric acid per 1 liter. So I'd get 1.4 liters of HCl. We're going to learn a faster way to do this particular problem in the next topic, and problems kind of like it. But it helps, I think, to do it this way just to sort of start to understand how molarity works. Okay, so this is a lot all at once, so I want you to try these problems. I will tell you, I think for most people, the hardest part is going to be those stoichiometry problems, so we'll work on those as a class when we get together. All right, good luck.